Here in this video we're going to be looking at the dynamic equilibria and altering conditions exam questions. So in this first question we are looking at hydrated copper sulfate, and we're told that this is a blue solid and that when heated we end up with our white anhydrous copper sulfate and water. And we're told that it's a reversible reaction, which we can also see by this symbol here. So to make the Ford's reaction work, the hydrated copper sulfate must be heated all of the time. So because we are requiring that energy, we need to be taking it in order for this to happen, then this is telling us that it is an endothermic reaction. Anhydrous copper can be used as a test for water. What two things will happen when water is added to anhydrous copper sulfate? So one of these things they've given us in the question. So we can see that our anhydrous copper sulfate is white, but when we add water to it, it's going to turn blue. So we would see a colour change from white to blue. And then also if we think about the fact that we know that we need energy to come in for that forwards reaction, that we require the heat energy, if we're going the opposite direction we're going to end up releasing heat energy, and therefore it's going to be an exothermic reaction. So the second thing that will happen is heat energy will be released as the reaction is exothermic. Okay, so then the second question, give the test and result for chlorine gas. So this is going back to our chemical analysis topic. So with chlorine gas we need damp litmus paper. Remember, it must be damp for that chlorine gas to dissolve onto the paper, and with this litmus paper it is bleached and turns white. The diagram below shows a sealed flask of sodium hypochlorite and hydrochloric acid at equilibrium. Now the fact that it's a sealed flask, this tells us that it's in a closed system. And so the question has asked us to explain why equilibrium is reached in the reaction. So this is only 2 marks, so we only need to be making 2 points. So our first point can be about it being a closed system and that no reactants or products are allowed to escape. And the result of that means that our forwards and backwards rates become equal. And of course that is what determines equilibrium being reached, is when our rates of our forwards and our reverse reactions are equal. So if we remove the stopper, it's no longer going to be in equilibrium because it's no longer a closed system. And then adding hydrochloric acid, that's going to cause our equilibrium to shift to produce or remove, and therefore have we got our reaction. So if we are increasing our amount of HCl, our equilibrium shifts to decrease it, and therefore it's going to want to use it up and therefore favour the forwards reaction. So it shifts to remove hydrochloric acid and thus favours the forwards reaction. And then this bit here, the stopper is replaced, and so a new equilibrium is established because that system then becomes closed again. So this next question is looking at the chlorine gas that's produced when hydrogen chloride decomposes, and it's told us our forwards reaction is endothermic. Predict the effect of increasing temperature on the amount of chlorine gas produced at equilibrium. So we have to use Le Chatelier's principle to explain this. So the easiest way to think about this is if we're increasing the temperature, equilibrium is going to shift to decreased temperature and therefore favour our endothermic reaction. So our forwards reaction is endothermic, so therefore we're going to increase our amount of chlorine. So our amount of chlorine gas increases as the equilibrium shifts to oppose the change, and so favours the endothermic reaction. Explain the effects of increasing pressure on the system. So here we need to look at the number of molecules on each side of this balanced equation. So on the left hand side we've got 2 for the 2 hydrogen chlorides. On the right hand side again we have 2, 1 molecule of hydrogen and 1 molecule of chlorine. So there is no change when pressure is increased because there is equal numbers of molecules on each side. Okay, next question. So sulfur dioxide is used to manufacture sulfuric acid. Explain why sulfur dioxide has a low boiling point. So this is a throwback to structure and bonding from last year. So we need to be thinking about the type of structure that sulfur dioxide has. So SO2 is a bit like CO2. And so what we know about carbon dioxide, again, it has a low boiling point. It has covalent bonds between the sulfur and the oxygen. But it's also existing as a small molecule. So it's not a giant structure, it's a simple one. So SO2 is a small molecule, and when we are boiling or melting SO2, we aren't breaking those bonds. So those bonds are very strong and they would require a lot of energy to break. But if we think about another small molecule that we're more familiar with, such as water, H2O is the molecule that exists in ice, in liquid water, and in water vapour. So that molecule does not change in those different phases. Those bonds remain intact. And it's the same for our sulfur dioxide. So these covalent bonds remain intact. But what does change is the distance between multiple molecules of sulfur dioxide, because we're not just talking about one molecule, we're talking about lots of the molecules. And so we talk about intermolecular forces that act between those molecules and hold them close together. But intermolecular forces are very weak, and so only a little amount of energy is needed to separate the molecules. So SO2 is a small molecule, and only a little amount of energy is needed to overcome the weak intermolecular forces between the molecules in order to separate them. Because if we're going to a gas, we want our molecules being able to move quickly, and therefore they need to be able to be moving away from each other. We need to overcome those forces. Okay, so the next question is looking at the manufacture of sulfuric acid from sulfur dioxide. It's a reversible reaction we can see from our symbols there, and we've been told that it's exothermic in that forwards direction. Use Chatelier's principle to predict the effect of increasing the temperature on the amount of sulfur trioxide produced at equilibrium. So if we increase our temperature, then equilibrium is going to shift to decrease our temperature and therefore favour our endothermic reaction, which takes in energy. And in this example, if our forwards reaction is exo, then our reverse is going to be our endothermic. So if our reverse reaction is favoured, we are going to be favouring our left-hand side, using up our SO3, and so we're going to be decreasing the amount of SO3. So amount of SO3 decreases because the equilibrium shifts to oppose the increase in temperature and therefore favours the endothermic reaction, which is the reverse reaction. Okay. Use Le Chatelier's principle to predict the effect of increasing the pressure on the amount of sulfur trioxide. So now we need to consider our number of moles, or number of molecules on each side. So on the left hand side we've got 2 sulfur dioxide and 1 oxygen, so 3 molecules there, but on the right only 2. So if we are increasing pressure, our equilibrium is going to shift to decrease pressure and favour the side producing fewer moles. So giving our reason for our answer, so fewer moles, we're going to be favouring the forwards reaction and therefore increase our amount of SO3. So there wasn't actually much space to write this answer here, but I'll just write it as concisely as possible. So increasing SO3 because there is a shift to favour our reaction producing fewer moles. Okay, a company manufactures ethanol, and we've got our reaction for that process there. So they've given us the enthalpy change here, so minus 45. So because it's negative, that shows us we've got an energy decrease going from our reactants to our products, and therefore energy is being released to the surroundings, and so it's an exothermic for that forwards direction, and therefore our reverse will be an endothermic reaction. So the first question we've been asked though is to explain what is meant by an equilibrium. So here we can talk about it being reversible, so it has a forwards and backwards reaction. But at equilibrium, we know that our rates are occurring at the same time. So forwards and backwards reactions occur at the same rate. And we should also state the condition that's needed for that equilibrium to happen, and that's that it's a closed system. Because no reactants or products can escape. Okay, how would increasing temperature change the yield? So whenever we look at yield, we're talking about Le Chatelier's principle. So if we are increasing temperature, then our equilibrium shifts to decreased temperature, and therefore will favour our endothermic reaction, as that will take in energy and lower the temperature. So in this example, our endothermic is our reverse reaction, and therefore our yield of ethanol, our product, is going to decrease. So yield decreases as equilibrium shifts to favour the endothermic reaction, which is the reverse reaction. Okay, and question 2, we're looking at pressure. So if we increase pressure, the equilibrium shifts to decrease pressure by favouring the side producing fewer molecules. And so if we return to our equation, we can see we have 2 molecules on the left-hand side, one of the ethene and one of the water, and on the right-hand side we have 1 molecule of that ethanol. So now our yield is going to increase as the equilibrium shifts to favour the forwards reaction, because it produces fewer moles. And therefore that would reduce the pressure. And then finally we're looking at about catalysts, which we know increase the rate of reaction. So explain how it increases the rate of reaction. So we looked at this with our catalysts questions. So it provides an alternative pathway with a lower activation energy. And therefore we have less energy needed for particles to react,